We're going to move on to a new chapter, chapter number 8, DC to AC inverters today. Before we do so, do we have any questions? Okay, so your quiz number 4 is graded. I have it here. After the class, I can return it back to you. The grades are on Blackboard. The average of the quiz was relatively high, 9.2 out of 10, and the only explanation is obviously you guys have got much smarter. The quiz for next week on Tuesday will be covering this chapter that we just finished, the isolated DC to DC converters, topologies such as the flyback, the forward, the push-pull, the full bridge, the half bridge, those kind of things. What we're going to do today is we are going to start talking about inverters. Applications for inverters are pretty much whenever you have an electric motor and that motor is an AC motor, like for instance an induction machine or a permanent magnet machine, those kind of things, a synchronous machine, those kind of things. The signal that you have to feed to this electric motor should be AC. Now what if you have a DC source, then the inverters come in? Or what if you have an AC source? For instance, you have the AC 3-phase or single-phase power available from the power outlet, but you want to do adjustable speed drive kind of a thing. That means what you have to do is you have to rectify the AC power that is available to you. So you do an AC to DC rectification. Then you do an DC to AC inversion. And in the inversion phase, in the second basically stage, you have the basically flexibility of changing the frequency of the signal or the voltage that you're applying to your electric motor, or changing the amplitude of the voltage that you're applying to your electric motor. Therefore, you can actually control the speed of your electric motor, something like that. So for instance, a good example would be if you have an electric vehicle, and in an electric vehicle, the energy that you have available as your source is a DC kind of a thing, because that's the voltage of your battery. But then you have a traction motor, which is pretty much a 3-phase synchronous motor, permanent magnet synchronous machine. So you need to have some sort of an inverter to do the job for you. Or another application could be has nothing to do with electric motors. If you want to send power, for instance, back to the grid. For instance, you have some solar panels installed on the roof of your house, and locally you use some of this, but then you want to send the rest of this electricity back to the grid. Your source is DC, your load in this case, which is the grid, is AC, so you need to have an inverter that converts this energy from DC to AC. Inverters are, you can categorize them into single phase and 3-phase inverters. First we talk about single phase inverters because obviously they are easier to study, and then we move on to 3-phase inverters. As it turns out, we have seen inverters in this class before, just the chapter that we finished, in topologies such as, for instance, full bridge or half bridge or even push-pull. What happens on the primary side of the transformer is you're generating an AC signal from your DC source using those, for instance, 4 switches or 2 switches and 2 capacitors, those kind of things, and apply it to the primary side of the transformer. So that's actually an inverter. So if you look at your, for instance, our class notes from last time or even the time before that, you know, when we had this push-pull converter over here, the primary side is pretty much an inverter. Or when we had this full bridge converter over here, oh, this is half bridge. This full bridge converter over here, if you look at the primary side, it's basically an inverter. It just inverts DC signal to an AC signal, a square-shaped AC signal. And that's what we are going to do today as well. So pretty much what we are going to analyze as our single-phase H-bridge inverter is this block over here on the left-hand side. Okay, so I have it over here. As you can see, we have 4 switches, 1 DC source, and some sort of a load, which is shown over here as like this block or this box over here. So this is basically your load. All right. So we don't know what the load is yet. We just know something is consuming power over here. This load could be a resistor, could be, for instance, the winding of a, for instance, electric motor. So most likely it could be modeled with a resistor placed in series with an inductor, or could be the power grid, something like that. So whatever is consuming our power. So as you can see, we have 4 switches, and later on we are going to talk about the realization of these switches. Are these switches really diodes or switches? What exactly are they? We are going to talk about them later. But each switch has 2 possible, basically, states, on or off. So we have 4 switches, so we have 2 to the power of 4 possibilities over here. Some of them are not really viable possibilities. For instance, I cannot turn S1 and S4 on at the same time, because if I do so, I'm actually providing a short circuit path for my source, and that's actually violating KVL. So we don't want to do that. So some of these states are not really viable states out of these 6 states. If you cross those unrealistic states out, you can realize that there are only 4 states that make sense. One state would be S1 and S2 on. Okay, so if I turn S1 and S2 on, and obviously when I don't talk about the other 2 switches, the assumption is that they are off. So if I do so, I have a short circuit path here, and I have a short circuit path here. Okay, so we have kind of a loop like this. And if you see our output voltage, we don't know what the load is, but we can measure the voltage that appears across this load. The output voltage will be VDC. So let me just erase this and then continue writing. VDC, or in my notes, I'm using VN as the input source voltage. All right, so this is one possibility. So sometimes we can apply positive voltage to our load. The other possibility is if I turn S3 on and then S4 on. So now we are looking at this loop. All right, if you look at KVL at this loop, you realize that your output voltage is the opposite of the input voltage, or V out plus VDC should be 0. So if you turn S3 on and S4 on, we can apply a negative voltage to our load. Okay? And there are 2 other states that are almost identical, and that is, for instance, if I turn S1 on and S3 on, so technically I'm actually closing this loop over here. So in that case, you can argue that you can apply 0 volts to your load, or basically you can short circuit your load. So if I have S1 on and S3 on, V out will be 0, and Vn, or the source, is actually not really engaged. Similar to that, I can turn S2 on and S4 on and create a short circuit loop over here, or short my load through instead of S1 and S3, I can do it with S2 and S4. Gives you the same results. So the 4th mode is S2 on, S4 on. Then again, V out will be 0. Okay? And the source is not really engaged. So I know, looking at these possible modes, viable modes, sometimes if I want to, I can apply a positive voltage to my load. Sometimes I can apply negative voltage to my load, and sometimes I can apply 0. So the rest is up to us, which one we want to choose. For instance, the very first switching scheme that we are going to choose is we only use the first two possible states, that applying Vn or negative Vn across our load. We don't even use the 0 one. And then later we are going to introduce the 0 level as well. So we have all these possibilities. It is up to the, you can call it the modulation scheme or the switching scheme. It's up to that scheme to decide which one of these modes we are going to choose. So the very first mode would be, let me see if there's a name for it. Yeah, a square wave inverter. Okay, so if you select to do this switching scheme, which is labeled like this, the output voltage that we desire to generate looks like this. If this is one switching period, this is half of that. And during the first half of the switching period, we choose in unit state number 1 or apply positive Vn to our load. And for the second half, we apply negative Vn to our load. All right, so let me clear this a little bit. All right, as simple as that. I don't even bother with the 0 level at all, but later we're going to talk about why we can use that 0 level as well. So somebody may walk in and say, yeah, let's do it this way. We have define a switching period, then divide that switching period into 2 equal halves, and then during the first half, apply, turn S1 and S2 on and apply Vn across your load. And during the second half, turn S3 and S4 on and apply negative Vn to your load. And you say, yeah, no problem, we can do that. As you can see, the signal that we have generated is AC. It's not sinusoidal, but it is AC with an average value of 0. Okay, so this kind of continues like this. All right, so let's just focus on this. Let's just focus on this case of we are doing this square wave inverter. Now, as soon as we determine our switching scheme, or in other words, which one of these switching states we are choosing, then the question is, what kind of load are we using? And if we identify the load, the next question would be, what would be the current waveform look like, the current of the load, for instance. So now I know what my output voltage looks like, but I don't have any information about the output current. Before doing so, I have to determine basically the dynamic of the load. So let's say our load is an RL load. All right. Obviously, if my load was just a resistor, then the current and the voltage waveforms were proportional with each other. Now, if it is an RL load, things are going to be a little bit different. And the reason that we are interested in RL load is if, for instance, we are driving an electric motor, most likely the winding of that electric motor could be considered a resistor placed in series with an inductor. So that's why we are most of the cases, interested in RL loads. All right. So technically, the schematic of the system, now that I know what my load is, looks like something like this. Let me see if I can find a nicer picture. Well, no. All right. So it looks like something like this. So the power stage did not change, just we identified the load. And the load is a resistor placed in series with an inductor. And please remember, output voltage is not just the voltage of the resistor, it is actually the entire load voltage. Okay, from here to here. All right. And the switches are the same, they are labeled the same. S1 and S2 are a pair, and then S3 and S4 are a pair. And as I explained, the switching scheme that we are using is in mode 1, or the first half of the period, we turn S1 and S2 on, and therefore V out is the same as V in. And for the second half, we use S3 and S4 on, Therefore, V out is the negative, the opposite of Vn. So if you look at your output voltage, I just drew it earlier, it looks like this. Okay, something like this. All right. So we already know what the voltage looks like. Now let's focus on finding the output current. So what we are interested ultimately to find is this current waveform. The current that passes through our resistor as well as our inductor, and they are both parts of our load. As it turns out, this is the waveform of output current. I'm going to draw it, then I'm going to explain where I got it from. Let me see. It's like this. It's not really triangular. These are exponential terms. So please pay attention. This is not a straight line. There is a little bit of a curve to it. This one as well. Okay. So we want to have a clear understanding of how our output current looks like. All right. So let's look at each individual mode. So for instance, let's take a look at mode number 1. We just talked about in this mode, S1 and S2 are on. So if you look at the equivalent circuit, this is S1 shorted. Then we have the load. And then this is S2. And this is our source. And I did not draw S3 and S4 because they're open. And this is our output voltage. So we have a very simple loop. Going back to circuits 1, you can write something like this. You apply KVL around the loop, and you would say the voltage drop across the resistor, which is this term, plus the voltage drop across the inductor, which is this term, has to be the input voltage. All right? So you have a very simple differential equation to solve, and let's say you already know how to solve this, and this is going to be your response. All right? So we have like a steady state response, which would be V in over R. Okay, and then we have like an exponential transient response, which is an exponential term, and it's determined by this second term that I have here, A, which is a constant, and we have to figure out what A is, and e to the power of negative t over tau, and tau is basically the time constant of the inductor and the resistor. All right, we have seen this in circuits 1 basically. All right. So this is all we can find so far. Then later on, we have to find A, which is actually determined by the initial conditions in the system. So this is mode 1. What about mode 2? In this mode, we are turning S3 and S4 on. All right, so now the circuit looks like this. All right. So again, if you apply KVL, it's almost the same equation. Except that it's negative V in this time. It's like we are changing the excitation to the system, and then you can find another response, which is negative V in over R plus another constant, I just name it B, times e to the power of negative t minus t over 2, the whole thing divided by tau. All right. Since this state is happening at time equal to t over 2, t being the period, the switching period, so everything is kind of shifted. The first one was happening at time equals to 0, so there is no time shift in the first exponential term. And tau is the same, L over R. And again, you can see that if you just leave the system by its own for a long time for this, you're going to realize that the dynamic of the inductor is going to damp down, and the current is going to be negative V over R. But there is a transient as well. So, and this is actually, when you draw these, this is the first exponential term, and which is V over R plus A, the exponential term, and this is actually the second one in the second mode, and this is obviously T over 2. All right. So now we got to find A and B, the constants. Okay. Any questions so far? All right. And before we go forward, let me just label this to be equation number 1, and this one to be equation number 2. Okay. So in order to find A and B, we can actually consider a bunch of things. One of them is, when I started this process, let's say I have been running this for quite some time, and I have already reached a steady state. So when I start the first mode, my current starts from some minimum value and then rises to a maximum value. And because this is periodic, then at the end of the cycle, again, it falls back down to a minimum value. So let's assume this really exists, this steady state behavior exists, and then we can write a bunch of equations. So basically, we are saying that the output current at time equals 0 is like a minimum value. All right? And the other one is the output current at the middle of the switching period is a maximum value. And also the output current at the end of the period returns back to where it started. All right. So we use this actually to find these A's and B's. So for instance, from this very first one, if I know this, and also consider equation number 1, together you can say that A turns out to be I min minus Vn over R. We don't have I min yet, but later on we have to find I min. Or also using the second equation, that I out at T over 2 equals some maximum value, and use it in the second equation, you can conclude that B equals I max plus V over R. Okay. As it turns out, A is like a negative thing, negative value. I don't have a proof yet, but later on, I just want to bring this to your attention, but later on you can double check this. A is negative and B is positive. Okay? Okay, so now what we can do is we can actually look at equation number 1 describing the operation in the first mode, and equation number 2 describing the operation in the second mode, but there's overlap. There's an overlap between these two modes, and that is T equals to T over 2, period over 2. So if you look at the output current at T over 2, you can either use the first mode equation, which is equation number 1, and conclude that V over R plus A e to the power of negative t over 2 over tau. This is if you use equation number 1. Or at the same time, you can use equation number 2 and claim that they are basically the same thing. All right? So this is one equation that you can find between, one relationship you can find between A and B, or I min and I max. The other one is, I'm looking at the behavior under steady state conditions, meaning that at the beginning of the cycle and at the end of the cycle, I should have the same amount of current. So at the beginning of the cycle, I can use equation number 1. At the end of the cycle, I can use equation number 2, which gives me okay, something like this. Just make sure, yeah, we have a negative there. Okay. So again, this comes from equation number 1, and this one comes from equation number 2. All right. So now I have two relationships. They are independent of each other, but at the same time, A and B appear in them, which are the two unknown parameters. So you can actually solve it and conclude a bunch of basically conclusions. One of them is, before we go there, let me create some space down here. Oh no, actually we are doing good in terms of space. So one conclusion could be A is the opposite of B, or I min and I max are actually the opposite of each other. So the indication is our output current waveform is kind of a symmetric thing. There's the other is actually the solution for A and B, but I don't have the solution for A and B. I just have the solution for I max and I min. Which is Vn over R times 1 minus e to the power of negative t over 2 tau divided by 1 plus e to the power of negative t over 2 tau. All right? So if you have the parameters of the system, for instance, the value of the inductor, the value of the resistor, the value of the input voltage, therefore, if you use this equation, we can actually find the maximum and minimum values of the current, and by the way, they are opposite of each other. So it's quite simple. All right. I don't expect you to memorize this equation. Just remember this equation exists, and somewhere, have it on your notes so that later on you can use it. So I already had the waveform for the output current, and so now that I have I mix and I min, for sure we can argue that the output current looks really like this. There's an exponential term going from I min to I max, and then comes down, and then comes up, and then comes down, something like that. All right? So this is our output current. Now one may ask, okay, now that we have the current waveform for the output current, what about, for instance, the current waveform of our switches? For instance, switch number 1 and switch number 2. So if you look at the way we turn things on, in the first mode, switch number 1 here was on, and switch number 2 over here was on. Otherwise, these switches were off. So in the first mode, the current of the switches and the current of the output are the same, otherwise they are 0. So when it comes to drawing the current of the switches, they follow the output current in the first mode, and in the second mode, nothing is going on for these two switches. And same here. Okay? So this is our switch current waveforms. The other two switches are almost the same, only 180 degrees phase shifted. In the first mode, 3 and 4 were off, so nothing going on here and here. But in mode 2, it is actually following the opposite of the output current. So let me actually explain that. The way the polarity of the current of these switches are defined, they are all going from top to bottom. It's very important to define this direction first. All right. So in the second mode, for instance, this is switch number 3. Okay, this is the current of switch number 3. It is the opposite of the actually output current. So whatever output current I had to flip it to be able to draw this waveform. Okay, so please remember this is like this. All right. Now that I have the switch currents, I can look at the source current, because if you look at the source current over here, the input current is IS1 plus IS3, or it is IS4 plus IS2. So all I have to do is just add up these two waveforms with each other, and then that's my actually input current. So it's going to look like this. All right, something like that. So this is our input current. All right. As you can see, the input current is sometimes positive, it is sometimes negative. So if I'm actually using this inverter in an application, I should be mindful that my source should be in a way that it can, obviously my source should be able to basically supply some current to me, but also it should be able to sink some current. So if your source is a PV panel, it's not going to work unless you put a capacitor in parallel with your PV panel. So when it is actually sinking current, the current is not really going back to your panel, it's actually going to that capacitor that is placed in parallel. And the other thing that you have to be careful about, and we're going to talk about it when it comes to switch realization, is switch currents are bidirectional. Sometimes before all of the switches that we have seen, for instance, just envision the switch current in a buck converter or in the boost converter. They're always positive or zero. Here, the currents of the switches are sometimes positive, sometimes negative, and sometimes zero. And that's actually an indication that the switch realization is going to be different, that we're going to talk about. So keep that one in your mind as well. The other one is always this power equation, that the input power is the same as the output power. On the input side, we have a DC source, so the input power is the value of this DC source times the average value of the input current, which is this expression over here. On the output side, we have an inductor that on average doesn't consume any power, and basically we have to just focus on the resistor. And the power dissipated in a resistor is the current of the RMS current of the resistor squared times the value of the resistor. So this equation sometimes comes in handy. If you, for instance, have the RMS value of the output current, you can easily find the average value of the input current. Or if you have the average value of the input current, you can easily find the RMS value of the current of the output. All right, any questions? So quite simple. It's basically circuits 1. We just have two exponential terms, and they have to operate with each other under steady state conditions. Okay, if there are no questions, we're going to have a numerical example now. So in this numerical example, we have a DC source that is 125 volts. So remember, this is a DC source. The frequency, the switching frequency is only 60 hertz, which is like the grid, frequency. So there is some application that we are doing things at low frequency. The load resistance is 20 ohms, and the inductor value is 20 millihenries. Please note that all of a sudden, because the frequency is so small, the value of the inductor is very, very large. If you consider your buck converter that was operating at 100 kilohertz, the inductor that you needed usually was in the order of, for instance, microhenries, like 20 micro, 30 micro. Over here, your switching frequency is only 60 hertz, and all of a sudden your inductor is in the order of millihenries. So that means it's a very bulky and a large inductor. Part A, determine an expression for the load current. Okay. So in order to find an expression, that means basically we have to go back to these equations and find all the parameters that are missing. Equation number 1 and equation number 2. So remember, in equation number 1, for instance, Vn and R appear, we can just plug the numbers, but also A appears, we have to find the value of A, and also tau, which is L over R, so we have to calculate all of them. So if you do so, first thing that you can do is actually find I max and I min. So we just had the expression for that. So this is, by the way, Vn. Okay, let me write it here. We just had it up there. Vn over R, 1 minus e to the power negative tau. Okay, so you pretty much have all the parameters that you need. T is the switching period, 1 over 60. Tau is L over R, which is 0.001. And you can actually, because twice we are using e to the power of negative 2 over tau. So actually, as it turns out, this is like 2.4 times 10 to the power of negative 4. So you have pretty much everything, and you realize that I max turns out to be 6.246 amperes, and obviously I min is the opposite of this. All right, so we have I max and I min. From I max and I min, you can, for instance, find A and B. Okay, we had this expression over here. Where was that? So for instance, when you have I min, you can plug it over here and find the value of A. And using I max over here, you can find a value for the numerical value for B. All right, so let's say you have already done this. So we end up with these expressions. Let me just rewrite these expressions. They're a little bit messy over here. So if you want to have an explanation or expression describing your output current, remember in the first mode, the output current was a kind of a forced response, which was Vn over R. In this case, Vn is 125 and R is 20, so that gives me 6.25. All right, plus some exponential term that was A times, so this whole thing is actually A. I min minus Vn over R. We just found I min, we have Vn, we have VR, we have R, we can easily find that. So this would be, as it turns out, and I mentioned it earlier, A is a negative value, so it's a negative 12.497 e to the power of negative t over tau. Tau is 1 over 1,000, so 1 over tau is 1,000. All right. So this is when my inductor current is kind of going up like this. And the other case, I out, was negative Vn over R, so it's negative 6.25 plus B. B turns out to be a positive value, which is the opposite of A, 12.497 e to the power of negative all right. So e to the power of negative, so remember the expression, negative t minus capital T over 2 over tau. Okay. Here it is. Equation number 2. So we had t, which is our variable, negative minus half of the period over tau. So division by tau is multiplication by 1,000. Then t, which is the switching period, is 1 over 60, and then half of that is 1 over 20. So that's actually how it looked like. And this is happening between, the first one is, oops, and the second one is valid for the second half of the switching period. All right, something like that. So this is an expression for our output current. And it just comes down like this. All right, so quite simple. Any questions?
Why do we assume that at steady state, like the I min will be same at 0 and t and like?
Okay. If you don't assume that, you will be analyzing the transient response of the converter. But most of the time, at least as far as this course is concerned, you neglect the transients because honestly, like for instance, when you turn an electric motor on, a speed moves on from 0 to some, I don't know, 1200 RPM. So we only care about that ultimately what the response is going to look like. That transient only happens in a short period of time. If we realize that this transient is actually hurting us, for instance, it's drawing a lot of current from our source, we can actually control the transient. So if you focus on the transient response as well, so it's going to look like this, for instance. If you zoom out, it is going to look like it goes up, then comes down a little bit, then goes up, then comes down more, then goes up. So ultimately, it goes to a steady state response. So we only care about the steady state response. Not that transient is bad. Actually, transient is bad. A lot of times, it may actually hurt us, but it's happening in a short period of time. So you can actually manage to do some soft, start or soft switching or whatever it is to ride through the transient without hurting anything in the system and get to the steady state. Other questions? Okay. So, okay, this example also have other parts. Part B is asking about what is the RMS value of the output current. Okay. So now we have an expression for the output current. We know it's periodic. One way of doing that is we can break it down to its Fourier series components and then find the RMS value, or just go with the very original definition of the RMS value of a periodic signal. It's the signal squared by, multiplied by itself, then take the average value of that over one period, and then take the square value of the whole thing. All right. As it turns out, because our signal is symmetric, we can actually do this thing for not the entire period, only for half of the period. So that's actually the second expression, is because our current waveform is symmetric in a sense that if I get the square value of this blue part and also take the square value of this red part, they are identical. So instead of doing it for the entire period, I can just do it for half of the period. So the math is going to be a little bit easier. So all I need is basically this first expression over here, because the second expression I don't need it because of the symmetry. So 1 over 20, which is 2 over t basically, and 1 over t over 2, which is t over 2, which is 120, integration from 0, and this is the expression that we had up here. Basically, it's coming from here, and then remember there is a power of 2 over here, so you have to multiply the signal by itself. And okay, I haven't really done the details over here, but as it turns out, the RMS value is 5.45 amperes. All right, so this is the RMS value of the output current. Then it is asking about the average value of the input current. So remember, there is an easy way of doing that. The easy way is, now that I have the RMS value of the output current, I have the value of the R, I have the value of the input voltage, I can easily find the average value of the input current. But let's say I don't want to do that. I have lots of free time. I just want to mess with this math. So the average value of the input current, again, if you look at the input current waveform, it's actually periodic with a period of t over 2. So I don't really have to do from 0 to capital T. I can do from 0 to capital T over 2. So that's what I'm doing here. I'm just only focusing on this part and finding the average value of my signal. And going with the original definition of the average value of a signal, then there is a symmetry in the system, so I only focus on the first half of the period. And this is the expression, for my in input current, which is the same as the output current in this mode, and the average value of the input current turns out to be 4.77 amperes. You can verify your answer by this equation that we had earlier, that input power is the same as the output power. So if you are interested in finding the average value of the input current, that's equal to load resistance times the RMS value of the output current squared. The whole thing is output power divided by the input voltage. So that would actually give you the same value. You can verify that. All right, so this was a numerical example. Pretty much everything is simple, straightforward. And let's talk about switch realization. Switch realization means we know what kind of voltage and current the switch has to be able to handle. What is the physical implementation of the switch? Is it an IGBT? Is it an IGBT in parallel with a diode? Is it an IGBT placed in series with a diode? Those kind of things. So if you look at the current waveform of switches 1 and 2, you realize that in the first mode, the current of these switches is the same as the output current. In the second mode, it's 0. All right, a waveform like this. We just talked about it earlier. So because my switch is sometimes handling positive currents, sometimes it's handling negative currents, if I want to use a MOSFET for this switch, I can use just a MOSFET because I already know that MOSFETs have this anti-parallel diode with them. So remember earlier in this class we said there is no way you can find a MOSFET that does not have this anti-parallel diode. And in this particular case, as you can see, this anti-parallel diode or the bulk diode is helping us. So whenever the current, for instance, is negative, this diode could be the component that is conducting. Or if I want to use an IGBT, I should definitely select an IGBT that actually has this anti-parallel diode with it. All right. So if you want to implement these devices, there should definitely be a diode in reverse, in parallel with your switch. It could be the embedded diode in your MOSFET, or if you're not happy with that diode, you can actually buy also an external diode and put it in parallel with that. Let's say the internal diode is not a good diode. For instance, it's not very fast, or it is exhibiting a lot of losses or things like that. You can also have an external diode as well. So this is external. This one is internal. All right. And as it turns out, S2 current and S1 current are the same. So when it comes to realizing S2, it's the same thing. For S3 and S4, again, the same thing. So if you actually draw your circuit diagram with all of these switches, it should look like this. Now, I'm for instance, assuming that I'm using IGBTs. So this is switch number 1, switch number 4, source. This is our load, and same thing over here. All right, so this is actually the physical realization of your ideal switches. Now, let me just go back and label these. So this is, let me call it, for instance, transistor number 1, transistor number 2, diode number 1, diode number 2, and which one was the third one on top, I guess? Yeah. T3, D3, T4, D4. Okay? So if you are curious about at what time which one of these components is conducting. So you can actually look at this and say, okay, I'm looking at, for instance, my output current. Which looks like this, okay, in one period. Okay. When the output current is negative, but still remember we are in the first mode, so there should be conduction for S1 and S2. That means D1 and D2 are on. So from here to here, D1 and D2 are the ones that are on. Then the output current turns to be negative, it becomes positive, but still we need conduction here and here. So that's actually going to give us that this is the right time to turn T1 and T2 on. Okay? Then my drawing is not very good because this length over here should be the same as this length, but it is not, unfortunately. But anyway. Let me fix it. All right, something like this. All right. Now, if you look at this mode, we are in mode 2. So we need a short circuit conduction path here and also here for S3 and S4. But the diode, the current is positive. So that means D3 and D4 are going to be on. And for the remaining, we are still in the second mode, but the current is negative, and that negative current could be conducted through T3 and T4. Okay? So if somebody says, oh, draw me the current waveform of diode number 1, you should be able to do that. For instance, if you are interested in current waveform for diode number 1, all right, a common mistake. They look at the output current and just draw it like here. And that's not true because the current of the diode always should be positive. So please remember, the output current is negative. That means in reality it's actually in this direction. Okay, so that's actually current of diode number 1 in the first mode when diode number 1 is on. So it's basically this portion multiplied by -1. Okay, so this is it. So this is the current waveform for diode number 1. Or, I don't know, current waveform for transistor number 1. Again, remember, all of these currents should be positive. Transistor 1, it is actually this one. All right. By the way, we don't have a numerical value or expression for here, but you can easily find it because you have the expression for the entire current. You can see at what time it actually crosses 0. All right. Any questions? Okay. So this is when it comes to realizing these switches. So all of these switches are actually a transistor in anti-parallel with a diode, basically. When it comes to turning these transistors on, so you can see that this transistor should be conducting from here to here. But it doesn't really hurt to turn it on actually in this part because you have turned the transistor on, but it's not really conducting because the current polarity is going through the diode. It's not going through the transistor. So actually you have all this basically time span to turn your transistor on, which is a good thing. The other thing that later on we are going to talk about is, as you can see, this diode is turning off when its current is returning back to 0, and also this transistor is turning on when its current is starting at 0. So you actually have a little bit of a zero current switching mechanism going on here. We are not going to talk about it now, but later we are going to discuss it. All right, so the system is very simple. Another way of looking at the system is, remember, all of these waveforms that we drew are periodic waveforms. So again, Fourier comes in and say, oh, you have a periodic waveform. I can explain your signal through a bunch of, a series of sinusoidal signals. And then from there, we can also look at, for instance, the RMS value of the current, the frequency spectrum of this currents, something like that. So what we do now is we all agree that this is the voltage that we generate on the output. It's a square-shaped signal. It is periodic, and it's symmetric. So if you try to find a Fourier series of the signal, it's quite simple. It looks like this. First of all, you only have harmonics appearing at odd harmonics because the signal is symmetric. Symmetric in a sense that immediately at the half of the period, we are actually turning the polarity of the signal. And so we have only odd harmonics, and the amplitude of these harmonics is 4 times the input voltage over pi over n, and n is the order of our harmonic, like n could be 1, 3, 5, 7, those kind of values, times sine of n, again the order of our harmonic, omega, angular switching frequency, times t. So omega is 2 pi over t, or 2 pi f, our angular switching frequency in radians per second. And now we can actually say, I can actually remember we were using superposition when we had like a rectifier. Now I can say that I have a load. Let me draw it over here. We have this load to which we are applying a square-shaped kind of a waveform. Okay, something like this. Because this thing is a linear load, like for instance R and L are linear and they are time invariant, we can argue that I can use superposition. I can break this source down to a bunch of harmonics. For instance, the harmonic that appears at n equals to 1, and then the harmonic that appears at n equals to 3, and so on and so forth. And then look at the response of each individual subcircuit, for instance, the current over here, and then in the end, add up all of these responses together. So I can add, I don't know, call it I1, call it I3, then I out is I1 plus I3 plus I5 plus IN. Okay? So you break down your system into the components, the Fourier series components, look at each individual response, then use superposition, then add all of these responses together to find your overall response. And that is what we are doing. So I am labeling this term over here to be Vn. So Vn is the amplitude of the nth harmonic of the output voltage. All right? So therefore, I can rewrite my output voltage in this form. Bunch of amplitudes times sine signals. Then I can find In. In is the amplitude of the nth harmonic that appears in my output current, which turns out to be under steady state conditions, Vn over Zn. What is Zn? Z is the impedance of the load. Okay? So Zn is the load impedance. All right? And then I can reconstruct all of these terms with each other. Now, unfortunately, this reconstruction that I have over here doesn't really take good care of this angle over here, so I'm just going to rewrite it for you guys so you know what it is. is, so my output current would be the summation of all of these responses. So I have a sigma over n odd values for, let me just do it Vn. Okay, let's make it simple first. In sine of n omega t minus theta n. All right, it's very general form. Okay, and for I know In is Vn over Zn sine of n omega t minus theta n. And I'm going to define theta. And I also know what Vn is. Vn is the amplitude of the nth harmonic of the output voltage. It turns out to be 4Vn over n pi. All right. Okay, now what is theta n? Theta n is the angle of the current, which is like a phase lag all right, so if you have an LR system, this is going to be our phase lag, and as you can see, depending on n, the number of harmonic that you're analyzing, there's an n appearing over there, and Zn is the magnitude of the impedance, so it's actually the magnitude of the impedance evaluated at the particular nth harmonic. All right, so quite simple. Then I have all of the harmonics that appear in my output current. So another way of finding, for instance, the RMS value of this current would be looking at, for instance, IRMS is, remember, it would be something like this. For instance, I1 RMS squared. There is no I2. The next component is I3 RMS squared. So I look at the RMS value of the fundamental harmonic of my output current, get the square value of that, get the RMS value of the output current at the third harmonic, then get the square value of that, then add all of these square values with each other, and then take the square root of the whole thing. All right? Or, for instance, you can look at the total harmonic distortion, those kind of things, for instance, in your, for instance, output or in your output current. I have two expressions over here for total harmonic distortion. You can actually, it's based on the very original definition of the total harmonic distortion in the output voltage and also the total harmonic distortion in the output current. Remember, the total harmonic distortion was in the numerator we had all the RMS value of all of the undesired values, the components. And in the denominator, we had the RMS value of the desired component. So as you can see, the desired component is the fundamental harmonic. So V1 and I1 appear here. Then on top, we have the RMS values of the rest of the signal that we don't really care about. All right. So following this, you can actually do some numerical analysis, and actually we have an example for this over here, a numerical example which is basically almost, I think, the same numbers. No, they are different. So load is 10. So we have this square wave inverter that the load is 10 ohms. Again, inductor is a large inductor, 25 millihenries. The frequency, switching frequency is 60 hertz. The DC value of the source is 100 volts. And for instance, we have been asked to find the Fourier series of the output voltage. Okay, so remember, if I'm interested in the nth harmonic in the output voltage, it would be 4Vn over n pi. So for instance, if I put n equals to 1, and I already know what Vn is, which is 100, and 4 and pi are constants, it gives me 127.3. If I put n equals to 3, it gives me 42.4. If I put n equals to 5, it gives me 25.5 volts. So these are all the amplitudes. And obviously this is happening at the fundamental frequency, 3 times the fundamental frequency, 5 times the fundamental frequency. So in the end we have 4 Vn over n pi sine of n omega t. N should be an odd value. Okay. And as you can see, as n grows, the amplitude of these harmonics is actually is going down. It starts at 127, then goes down to 42, then goes to 25. So if you go to, for instance, harmonic number 25, it's almost basically zero, very, very small. Then we have been asked to find a Fourier series of the output current. So all I have to do is once apply this term to my impedance, find the current, then apply this term, then apply this term, and all of the responses that I get, I have to in the end add them together. All right. So now we are looking at our load. Our load is an impedance network of a resistor placed in series with an inductor. So if you look at the impedance of them, the impedances are being added with each other. The impedance of the resistor is just R. The impedance of the inductor is J, which is the square root of -1 times omega times L. All right. Now, if I am interested in evaluating this impedance at a particular frequency, I have to consider this equation. So Zn is the amplitude, because impedance by itself is a complex variable, right? So if I'm interested in the amplitude of this at a particular frequency, well, I have to plug that particular frequency here. That's why n appears here, and then take the magnitude of this complex variable. And In, which is the amplitude of the nth harmonic in the output current, is Vn, which is the amplitude of the nth harmonic of the output voltage, divided by Zn, which is the amplitude of the impedance evaluated at that harmonic. So we pretty much have all of these numbers. For instance, so Vn is 127 over n. N is the number of harmonic. And Zn is 100, which is our load multiplied by itself, 10 to the power of 2. N, order of my harmonic, omega, which is 2 pi, 60, and times L, 25 milli. And the whole thing is squared. Okay? So if you do that, you are going to end up something like this. So I'm going after the general case that I haven't even chosen a particular value for n. In general, it is actually telling me. So if I place n to be 1, the first harmonic in my output current, it turns out to be, the amplitude turns out to be 9.27. What about the third one, n equals to 3? It gives me 1.42. What about the fifth one? As you can see, it drastically goes down. It gives you 0.53 amps. And you can see this is way smaller than the original one, the fundamental one, which is almost 10. And it's a good place to stop actually the math. Theta n, as it turns out, doesn't really make a big difference, because in the end we are caring about the RMS values of the signal. But if you want to do theta n, which is the phase shift of these components, is the inverse tangent of n L omega over R. So if I really want to write a clean I out would be I1 sine of omega t minus theta 1 plus I2 sine of, I3 theta I3 omega t minus theta 3 plus I5 sine of 5 omega t minus theta 5. All right? As I said, finding thetas doesn't really make a difference because in the end we only care about the RMS values, but sometimes it does. So in case you want to find theta 1, all I have to do is in this expression place n equals to 1. Or theta 3 is the same thing, just n equals to 3, and so on and so forth. And for I1 and I3 and I5, all you have to do is use this expression over here. And for the particular n that you're interested in, 1, 3, or 5, just plug in the n that you need. So if you do so, you will get a numerical expression like this. And unfortunately, I don't have the number of thetas because I don't really need them anymore. But remember, they are there. All right. So this is a numerical example expression for our output current. And the next question is, how much is our output current? So remember, in the previous case, in the previous example, we looked at the RMS value of the current in a different way. We used the original definition. Now, because we have this Fourier series of the output current, we can actually use that. So remember, on average, the output power is the value of the load times the square value of the RMS value of the output current. All right? So, again, going back to original definitions that we had for the RMS value of a signal, remember we had this definition. Or just in general, I don't know okay, let me just write it as it is. I1 RMS squared, I3 RMS squared, okay, right. Now, because we need it here, we need a square value of the RMS value. So this is square root goes away, and these terms all appear over here. So I have R, which is 10 ohms, and this particular one. So remember, I1 is 9.27, but this is the amplitude. If you are interested in I1 RMS, is 9.27 over the square root of 2, and that's actually what we have used over here. So this is I1 RMS squared, and then I3 RMS squared, then I5 RMS squared, and they all end up with 444 watts. Now, what's interesting about this analysis, you can see how much power each one of these harmonics is contributing. The fundamental harmonic is giving you almost 430 watts. The third harmonic is only giving you 10 watts. The fifth harmonic is only giving you 1.4 watts, and so on and so forth. All right, so one more thing. What is the total harmonic distortion of the output voltage? So go back to the original definition. What is it, the fundamental harmonic that we need? V1 RMS, and then in the numerator all the undesired components. So the fundamental harmonic is 127 volts peak value, so you divide it by the square root of 2 to get the RMS value, and the rest are basically the undesired part, which is the RMS value of the entire signal, which is 100 squared, minus the rest of the first fundamental harmonic. Okay, so this gives you about 48%. Okay, and as it turns out, it is independent of the load. So if the total harmonic distortion of the output voltage is not actually quite good, because it's easy to do that, because our output voltage is not really sinusoidal. It's actually a square shape. What about the total harmonic distortion of the output current? Let me just write it over here one more time. I3 RMS is the first term that we don't need. Then I5 RMS is the second term that we don't need. Then I7 RMS squared. These are the things that we don't need, divided by the good one, which is I1 RMS. So we have all of these terms, I1, I3, I5, I7. In the end, this turns out to be 16.7%. And you kind of expected that because you have actually like a low-pass filter applied to your output voltage. So things are going to get closer and closer to a sinusoidal form. As you can see, your output voltage had a total harmonic distortion of 48%, but your output current is actually doing much better, only 16%. So, and remember, in electric motors, voltage doesn't matter, it's always the current that matters because current generates torque. So if your current is close to a sinusoidal signal, you can claim that I can ideally assume that everything is sinusoidal and my electric motor is operating at its best conditions. So here, as you can see, you can actually claim that your current only has 16% of total harmonic distortion, which is okay. It's not as bad as we think. All right, I'm going to stop here. Next time, we are going to introduce another switching scheme. But before we do so, I have a MathCAD file which is already on Blackboard. If you are interested, take a look. We are going to go through this briefly next time, which is kind of what I did on the paper. On my notes over here is like a computer program kind of a thing that does the exact same thing. So see you next week on Tuesday, and there's going to be a quiz on Tuesday.